What are exact trigonometric values? Okay, so we know the word exact usually in maths means either integer values, or surds. So that's the first part, trigonometric values. So we also know that in a right angle triangle, we have three trigonometric functions. We have sine, we have cosine, and we have tangent. Now, sine is the ratio or the quotient of the opposite side of the hypotenuse. Cosine is the adjacent over the hypotenuse, and tangent is the opposite over the adjacent. So, exact trigonometric values are either integer or surd values of quotients for sine, cosine, and tangent for specific angles. And there are two ways to use these. The first way is to remember them, and we'll talk about that later. And the second way is to remember how to derive them, and we'll do that as the second part of this topic. Now, because of the way they're derived, these angle values, or the trigonometric values for these angles, are for the same set of angles. And those angles are 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. So when we speak of exact trigonometric values, we are looking at the trig values for 0, 30, 45, 60, and 90 degrees. The first way to use them is to remember them. Now, the problem with that is that many of them are very, very similar. They use similar numbers in different forms, and it is difficult to keep them separate in your head. It also means that you are literally only remembering certain values in a one-to-one mapping between angle values and their quotient value, which isn't really the greatest way of understanding trigonometry. But for those of you who want to remember them, this is what they look like. So as you can see, several have the same numbers. Okay, sine for 0 is 0, cos for 90 is 0. Some don't have any value at all, as is in the tan of 90. What does that line mean? And some of them have surds as fractions, but they're either the same, or sometimes they're upside down, or all sorts of horror stories. So, as I said, you can remember them, but it's much better to know how to derive them. To derive from first principles, we need to understand how trigonometry works. And to do that, we're going to start off with the easiest angles, which are the 0 and 90 degree angles, and we're going to look at sine. Okay, so we know that the sine of an angle, and we'll call it theta, is defined as the quotient, or divided by opposite over hypotenuse. Okay, so, and we know that that's true for any right angle triangle. So there's our right angle, there's our hypotenuse, there's our opposite. Okay, so let's consider an angle theta. Okay, so we're going to start off with theta as 0 degrees. Now, we can't draw a triangle with theta as 0 degrees because the two arms of the triangle would be on top of each other. But we can draw a triangle that's very close to having an angle of theta degrees. So it would look like this. Okay, so we'd have our triangle. Okay. There's theta. There's the right angle. This is the opposite, which is a vertical line. And there's the hypotenuse, which is the longest line. Now, what we want to consider is theta tending or moving towards 0 degrees. Okay, moving towards 0 degrees. Now, as it moves towards 0 degrees, you can see that the hypotenuse will become lower. Now, as it becomes lower, it will become slightly shorter, but it will still be the longest side in the triangle, because it always is. But what you will notice is that the opposite will become much, much smaller. And as the hypotenuse approaches the horizontal line, which is the adjacent line, it will ultimately collapse on top of it. And at the point that it collapses on top of it, the opposite will be 0. Okay, so as theta tends towards 0 degrees, the opposite and hypotenuse, okay, that will tend towards 0, whereas the hypotenuse will continue to be a number, won't it? Okay, and 0 divided by anything is 0. So as theta becomes 0, we have the opposite, 0 length, divided by a number, the length of the hypotenuse, and 0 divided by anything is 0. So that means we can say that the sine of angle 0 is going to equal 0. Okay, and that's our first principle. Now equally, we can do it the other way around. If we want an angle of 90 degrees, this time we're going to have a triangle that is exceedingly, a right angle triangle that's very, very tall, because this is our angle theta, here's our hypotenuse, and here's our opposite. All right. Now this time we want angle theta to tend towards 90 degrees. Now, as it tends towards 90 degrees, you can see that the hypotenuse line is going to become closer and closer to the vertical. And as it does so, it's going to shorten the adjacent line and it's going to pull the opposite line towards it. And as it does that, so as an example, if we drew an even closer to 90, okay, oops, it's very hard to draw. There you go. The opposite becomes much larger. Now it becomes much larger until theta is 90, when the opposite side is on top of the hypotenuse, or it collapses onto the hypotenuse. Then essentially they become the same length. Now when they become the same length, because this is getting bigger, you have opposite over hypotenuse, okay, equivalent to, so that's tending towards the same size as the hypotenuse, divided by the hypotenuse. And anything divided by itself is 1. So we now know that as we tend towards sine of 90, that would give us 1. And that's how we know our sine for 0 and 90. Now similarly, we can do the same for cosine or cos. So cosine, we know, is adjacent over hypotenuse in a right angle triangle. There's the hypotenuse and there's the adjacent. So let's consider the cos of 0. So cos of 0, 0 is a very small angle. So here's a very small right angle triangle. There's the adjacent, there's the hypotenuse, there is the angle theta. Now, as cos, or the angle theta, tends towards 0, okay, what can we say? So as 0 tends towards that, we notice that our hypotenuse becomes closer and closer to the adjacent. It's falling down on it, isn't it? Now, as it falls down on it, it's going to tend towards the same size as the adjacent, because ultimately the two arms, the adjacent and hypotenuse, are going to be on top of each other. Okay, so we have cos of 0. Okay, this is calculated by adjacent and hypotenuse, but the adjacent, okay, is going to tend towards the same size as the hypotenuse divided by the hypotenuse. And anything divided by itself is 1. So the cos of 0 degrees is 1. And then we do the same for the other side. We do a very steepy triangle again, so round up there. Okay, except this, there's the right angle, there's theta, hypotenuse, adjacent. Okay. Now this time, the angle is going to tend towards 90 degrees. So as it tends towards 90 degrees, the hypotenuse moves to the left. If you imagine a anti-clockwise arm on a clock, it tends to go this way, doesn't it? Because it's trying to get vertical, so there's that 90-degree angle. As it does so, the adjacent becomes smaller. Okay. So what we now can say is the cos of theta is equivalent to the adjacent tending towards 0. divided by the hypotenuse, okay? And 0 divided by anything is 1, so that gives us cos 90 degrees equals 0. Did I just say anything divided by 0 divided by anything is 1? That was wrong. Okay, so 0 divided by anything is obviously 0. So cos and sine are very similar. They just tend to be opposite, okay, because you're using the different sides, the opposite and the adjacent. But they both revolve around the hypotenuse. And the reason they go from 0 to 1, obviously, is because the hypotenuse is the denominator. And nothing can be longer than the hypotenuse. So you can never have the numerator being greater than the denominator. Now that's not true for tan, which we'll talk about next. So tan, or tangent, okay, tangent of an angle is opposite over adjacent. Okay, so in any right angle triangle, there's our opposite and there's our adjacent. Now, what have we done? Oh yeah, there's theta. So let's look at tan 0 to start with. Okay, so when the angle theta equals 0, we have a triangle. Let's see, so here's our triangle, there's our right angle, there's our opposite, there's our adjacent. There is theta. Okay, so as theta tends towards 0, whoops, there's an error, honestly. Okay, this hypotenuse line will become lower. Okay, it will move down as like the hands of a clock, yeah, coming down, which means the opposite will become smaller. So we have tan of theta, okay, approximating 2. So let's see. So the opposite is going to tend towards 0, divided by the adjacent, which isn't going to change size. So as it tends towards 0, 0 divided by anything is 0. So we can say, oh, that should be 0, shouldn't it? Sorry. So we can say the tan of 0 equals 0. Now, the next one is a bit more weird. And if you remember, in our table of values, tan of 90 had a weird line on it, didn't it? It had a dash, so there was no value. Now, the reason for that is quite obvious if you carry on with the method we're using. So there's our opposite, there's our adjacent. Okay, there is theta. Now, as theta tends towards 90 degrees, we already know that the opposite gets bigger and bigger and bigger. Okay, but this time, because it's not limited by the hypotenuse, as it gets that way, it's going to stretch the hypotenuse, isn't it? Okay, because the adjacent isn't going to change value. So if you think about it, the adjacent is the same size. So if this is getting bigger, the hypotenuse must be getting bigger. Oh yeah? Okay, so the opposite gets bigger and bigger and bigger, but it can never become the, what's his name, can it? It can never become the hypotenuse. So what we have then is tan of 90, okay, approximates to, as theta and theta gets bigger, as theta gets to 90, the opposite is going to tend towards infinity, because that line is just going to get bigger and bigger and bigger and bigger and bigger and bigger, okay? And that will be divided by the adjacent. So anything very, 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 very large, tending towards infinity, because remember infinity is not a number, that means the tan of 90, okay, will tend towards or become infinity itself, which is why we have that dash line. It's undefined. All right, so that's very different from cosine and sine, which obviously, because the hypotenuse and denominator are limited to between 0 and 1. So tan can be any integer value, any real value from 0 up towards infinity. Now, with all of this its derivation for first principles has depressed you, you don't really have to remember it this way. You can remember it as long as you can remember your trigonometric graphs, which you should know off by heart for GCSE anyway. Okay, so if we consider our graphs, let's see, we have theta, and let's see, we have sine theta, we have theta and cos theta, and we have tan theta up here, and theta here. Now, although right angle triangles we only consider between 0 and 90, okay, you should remember if you've done the unit circle video that we tend to define the periodic functions as a circle, so it's up to 360 degrees. So if we do, let's do 180, 180, 180, and then here's our 90, and there's our 270, and there's our 360. Okay, 270, 360, 90, 90, 180, 270, 360. Now, we said sine of 0 is 0. Sine of 90 is 1. So we'll put a +1 there. Okay, so it's there. We said cos of 0 was 1. So cos is up there and 90 is down there. And tan, we said, was tan of 0 is 0. But tan of 90 is infinity, which is so far off the screen you'll be able to find it. So we need to change this to plus infinity. Now, because they are symmetric and circular, they range between the positive and negative values for their limits. So +1, -1, plus infinity, negative infinity. Now, the way I remember it is sine theta, we use the S, means starts from 0. Okay, and the cos theta, the C, is comes down from 1. It's a cheesy way to remember it, and if you don't like it, don't use it, but that's sort of how I remember it. Now, sine theta and cos theta, because of hypotenuse being the denominator, are linked, and they are very similar. One's a translation of another. The way to remember them, if you're using a unit circle, is that a unit circle you can split into 4 quadrants, which means that in 360 you've got that bit, that bit, that bit, and that bit. And if you cut them up and assemble them into the trig graph, you have a periodic wave. So a sine wave, it doesn't go up as a straight line, it goes up like that. There's your first quadrant, there's your second quadrant, there's your third quadrant, there's your fourth quadrant. Okay, so similarly for cos, but if we're starting up here and come down, we can see that the wave's going to have to do something like that. Okay, so if you remember your graphs, you can see straight away what the sine of 0 and 90 is and what the cos of 0 and 90 are. Now for tan, it is a weird one. Okay, and literally you just have to remember this, because although it comes from the unit circle, you can't use this little trick to remember it. You have to remember it in that it does have 4 pieces, but some of them repeat each other. So it just looks like this. It goes up, and then it goes off towards infinity. And because it's an infinity, we have to have an asymptote represented by a dashed line, which says, I'm going to approach you, but I'm never going to reach you. And then it repeats again, except it repeats from down here. So it goes, oops, sorry, what am I doing? So from negative infinity, comes up, goes through here, and then it goes off that way, and this goes down there. And then it does it again from 270. This is an awful graph, but you can look them up, okay? And there's the other one. All right. So here you could see, if you're going to read them off, that that's there and that's there. Okay, but if you don't know about the graph, with the unit circles and the graphs, the first principles method is quite simple. So that's 0 and 90. So now we're going to look at 30, 45, and 60. Now, you can't use the graph to do these, really. You can get the sine of them, because if you think about it, let's use a different colour. If I want the sine of 45, well, there's 45. If I go up and go across, it's over here somewhere. Yeah, but that doesn't mean much to me. I don't know what that is. I'd have to draw this graph super accurate to even get a decent estimate for it. So I'm not going to use that method. All right. I'm going to use a slightly different method, which is a nice, elegant application of geometry and trigonometry. To start with then, we're going to look at 45 degrees. So we would like to know what the... Oops, I'm wearing blue. Oops, I'm getting off blue. Okay, we're sine of 45 degrees. We want the cos of 45 degrees, and we want the tan of 45 degrees. Okay, equals. Now, let's remember, trigonometry requires a right angle triangle. So if we're going to do this, the first thing we're going to need is a right angle triangle. Okay, there it is. What's the second thing we're going to need? Have you guessed yet? Of course, we need this triangle to have a 45-degree angle in it. Okay, so let's write that there, 45-degree angle. Now, what else can we do about that triangle? Yep, well done. If we've got a 90 and a 45, this has to be 45, because angles in a triangle have to add up to 180 degrees, or triangles enclose 180 degrees. What else can we say about this triangle? Yep, it is right angled, but it's something else. It has two angles that are the same, 45 and 45, so it's isosceles. Now, because it's isosceles, we know those two sides are equal. So the opposite and the adjacent are always going to be the same length. Now, if you remember the basics of trigonometry, it's that all triangles that if one has a 90-degree angle, if we extend them, we have similar triangles. So it doesn't matter, because we've got angle here, how big the triangle is. So we can pick any number we like for the sides. We don't have to use a specific one. We could even use algebra if we wanted to, but it's much easier just to use numbers. So let's say that is 1 unit long. Now, if that's 1 unit long, guess what? This is 1 unit long. Now, for trig to work for all three functions, we need the hypotenuse. So how could we work out the length of that hypotenuse? Yep, it's not all Greek to me or to you. We're going to use our old friend Pythagoras, okay? So, Pythagoras states the square of the long side equals the sum of the squares of the other two sides. So if we say that the hypotenuse is that, we know it's the sum of the squares. So 1 squared is 1, plus 1 squared, which is 1. 1 plus 1 is 2, and it's the square root. So this has to be root 2. And now you should be able to see where these surds come from. Okay, we've now got all three sides. So guess what? Magical. We can work out what these are. We know sine, okay, equals opposite over hypotenuse. So in this, we have the sine of 45 degrees equals, well, hang on. That's the opposite. And of course, we could do it the other way, because the other one's a 45 degrees angle. That's adjacent. That's hypotenuse against that angle. So now we have sine 45, opposite over adjacent, 1 over root 2. Cos equals adjacent over hypotenuse. Okay, so cos 45 degrees equals, shockingly, 1 over root 2. And tan equals opposite over adjacent. So the tan of 45 degrees equals, opposite is 1 over 1, which equals 1. And there are our answers. So sine of 45, 1 over root 2, cos over 45, 1 over root 2, and tan is 1 over 1, which is 1. Now, as I stand here full of the glow of, oh, genius that I've done this, I also realise I've made a bit of a mistake. And it's not a mistake so much, it's forgetting something about surds. Now, if we look at, let me do this, we've said sine 45 degrees equals 1 over root 2. And obviously cos 45 degrees is 1 over root 2 as well. But if you remember your surds, there's something about 1 over root 2 you should remember. Yep, you've got to simplify it. That isn't the simplest form because we're not allowed to have a surd on the bottom. So we need to do what's called rationalising the denominator. So for a full answer, we need to rationalise this. We don't want root 2 at the bottom. To get rid of the root 2, we're going to times it by root 2, because a root times a root gives you itself. And because we don't want to change the value, what we're multiplying it by has to come to 1. So we need the top to be root 2 as well, because root 2 divided by root 2 is 1. So actually, the answer is root 2 over 2. That is what you'll see on a calculator. So it's not that it's 1 over root 2 is wrong, it's just not in its simplest form. And in an exam, you could lose a mark. So don't forget that, like I forgot it. So, we've got now 30 and 60 degree left. Now, we're going to use a similar method to how we worked out what 45 degrees was for sine, cosine, and tangent. But can you work out how to do it? Okay, so let's see. We're going to have, what colour pen have we got? Black. So, we're going to have sine of 30, sine of 60 equals, we're going to have cos of 30 and 60, equals, and we're going to have tan of 30 degrees and 60 degrees equal. So to work out from first principles, we're going to use a method similar to the one we used last time. So, trigonometry, we need a right angle triangle to start with, don't we? So we're going to draw ourselves a nice right angle triangle. There we go. There we go. Now, 30 and 60 degrees we need. So let's say this one was 60 degrees. Magical. This one has to be 30 because the enclosure's got to be 180 degrees. So we've got a right angle triangle with the angles we need. Oh, we're cooking on gas here. Something must be right. And then we're sort of stuck, aren't we? Because the last one, we were able to name two sides as being the same length because it was an isosceles triangle. It's not an isosceles triangle here. So what are we going to do? So if we look at this triangle, what could we do? Well, we could draw that triangle reflected, couldn't we? We could draw it here because it would also have 60 and it would also have 30. Does that help us? What sort of triangle have we drawn now? Yep, have you realised? This is an equilateral triangle. And what do we know about equilateral triangles? All the sides are the same length. Now, some of you will go rushing in and start saying, right, well, they've all got sides of 1, and that means if we consider the vertical line a perpendicular bisector, that means we've got half on each side of it. And then we've got our two sides, blah, blah, blah. Yes, you can do that. But half is a bit of a pain number to use, so why not do what we were going to do? 1 is the easiest unit to use, so let's say that's 1 and that's 1. Now, if that's 1 and that's 1, what's the length of each of the sides of the equilateral triangle? 2. Okay, so by doing it that way, rather than letting the side be 1 to start with and getting a half, we've now got nice integers to use. And it also means it's very easy for us to work out the length of the vertical side, which is going to be the opposite side, or the adjacent side, isn't it? Depending on which angle we use. So what's the length of the perpendicular bisector? Well, this time we have the hypotenuse, so we're going to subtract, aren't we, in our Pythagoras? So it's going to be 2 squared, which is 4, minus 1 squared. So 4 minus 1 is 3, and then square root that. So this is going to be root 3. And that's it. Because now we've got all 3 sides, we can work out all 6 of these angles, can't we? So let's go. So we've got sine equals opposite over hypotenuse. We've got cosine equals the adjacent over the hypotenuse. And we have tan equals opposite over adjacent. And then we just got to work them out. So for 30 degrees, sine of 30 degrees equals opposite over hypotenuse. So we have to be careful here because the 30-degree angle's at the top, yeah, in one half of the triangle of the equilateral, one of the angles. So if we consider it, that's 30, so its opposite is 1, and the hypotenuse is 2. So 30 degrees is a half. Okay, so if we stick with the 30-degree angle, we're looking at it down from the top really, aren't we? So we've got the cos of 30 degrees. So for cos of 30 degrees, its adjacent is root 3. And its hypotenuse is 2. And then the tan of 30 degrees, so looking down again, its opposite is 1. And its adjacent is root 3. So there's those three. And then if we go from the 60 degrees, we can now, so we were looking at it, if you want, we were looking at it from the 30-degree angle, so we're sort of looking that way. Now we're doing 60, so we're sort of looking that way, aren't we? Oops. So we have the sine of 60 degrees equals, so the opposite is now root 3 over the hypotenuse, which is 2. The cos of 60 degrees is the adjacent. So the adjacent is 1 over 2, so a half. And then the tan of 60 degrees equals opposite, which is root 3, over the adjacent, which is 1 or root 3. And that gives us all 6 answers using one simple equilateral triangle. So there we have it. Okay, so deriving from first principles just requires some basic knowledge of surds and trigonometry. Okay, but in doing that, you're demonstrating a deeper understanding of the maths that surrounds this topic. Yeah, so yeah, feel free to remember them if you can keep them in your head. I can't most of the time, but I find this very easy. It's very easy and quick to draw these triangles and go, oh yeah, da-da-da-da-da, done. Now, next bit. What sort of questions are you going to get? Because the ultimate question has to be, why are we learning this? And before we learn it, we need to remember not to make the same mistake I made throughout the entire video, which is I forgot to rationalize denominators. So if we look through this, we can say, okay, I have a half, that's fine. Root 3 over 2, that's fine. Root 3 over 2, that's fine. A half, that's fine. 1 over root 3. Now that's not fine because we have a surd as a denominator. So, naughty naughty, although that is an answer, the simplified answer needs to be rationalised. So 1 over root 3 times, so root 3 on the bottom, which means root 3 on the top, because we need to times it by 1, so we don't change its value. So that gives us root 3 over 3. Silly, silly, silly Mr. Moss. Now, in terms of questions, they can range from the very obvious to the slightly more complicated. So the very obvious questions would be things like write down the exact value of sine 90 or the exact value of tan 60, okay? As soon as you hear that, you realise, okay, I've just got to either remember them or I've got to derive them, as we've just shown below. I'm not going to do those ones because they're obvious. You could get slightly more complicated ones where they talk about angles greater than 90 degrees. I'm not going to consider them here because that means you need to understand the unit circle and the idea of periodicity and the graphs, which are covered in the other video on this subject, okay? So I'm going to look more at the sort of questions in right angle triangles that you'd get that rely upon you knowing or be able to derive exact values. So, for example, you could have a question that looks like this. Okay, here's a triangle. Okay, you've got a hypotenuse of 8 root 2, and you've got this side is 4 root 2, and you've got to find out what angle x is. All right, so this could be a sort of question. Essentially, you're just going to do what you would do if you had numbers. Now, the reason this is an exact trig value, not only because they've got surds in, but you wouldn't get this usually in a calculator paper, so you wouldn't be able to do it with a calculator. Normally that's a hint that it's going to be trig values, okay, exact trig values, because you don't have a calculator to be able to work them out. But what would we do? We'd say, okay, we have a right angle triangle, we have two sides. So if this is our angle we're considering, then this is the opposite side and this is the hypotenuse side. Opposite and hypotenuse is the sine function. So we can write the sine of x equals opposite over hypotenuse. So that equals sine x equals 4 root 2 over 8 root 2. And then it's just some basic surd work. So sine of x equals 4 and 8 will cancel down, won't they? So there's 1 4 and 4, 2 4s in 8. Root 2 and root 2 will cancel down 1 and 1. So you have 1 times 1 over 2 times 1. So sine x is a half. And again, this is a non-calculator question, so you're thinking, okay, how do I know what the angle is? It's got to be one of the exact trig values, okay? And you should be able to remember what they are or derive them. So we know sine x is a half, so to undo sine, we have to do the inverse sine of both sides. X equals 30 degrees. All right, so that's one sort of question you may be asked. Here's another type of question in a similar vein. This time we're trying to find the side, aren't we? So we look at this. So if you ever stuck, just imagine that it wasn't a surd, it was just a standard number. And you can think, how would you do this? So you have the angle and you have to work out what side you've got. So you'd say, okay, well, this is the hypotenuse for 30 degrees. And this is the opposite for 30 degrees, isn't it? So in that case, we know we're going to use sine. So we're going to be able to write sine of 30 degrees equals, so the opposite is x over the hypotenuse. So that's 4 plus 5 root 2. Okay, so a bit of rearranging now. So x equals 4 plus 5 root 2 times the sine of 30 degrees. And then we need to remember what sine of 30 degrees is. Okay, so if we forget, we come over here and we draw a little sketch. We go, okay, 60 and 30. Let's remember, there's 60, there's 30. We know that was 2, that was 1. We remember that was root 3 from Pythagoras. So x equals 4 plus 5 root 2 times the sine of 30 degrees. So if that's 30, sine of 30 is opposite, which is 1 over hypotenuse 2. So it's a half. So, okay, times a half. Oops, times a half. So x equals, well, 4 times a half is 2. And 5 times that is plus 5 over 2 root 2. Which is quite ugly, but then sometimes the answers are going to be, aren't they? Because you're not using a calculator. But remember, exact trig value, the more complex questions, will end up really being surd questions. Yeah, you either get surd or integer answers, or you'll be manipulating them using 4 operations and the basic trigonometric functions that we remember using SOHCAHTOA. So don't freak out when you see things like this, okay? When you see the surds, when you see angles, you think, I haven't got to calculate, what am I going to do? Once you understand that it's exact trig values and you remember or can derive them, it is very basic surd work. There are more complicated ones, but I'll deal with those in a different video. Next sort of question you may be asked is just to add or subtract or BIDMAS for operations the various values, okay? So you could be asked something that's, say, what is 45 degrees plus sine of 45 degrees? Now, the one thing you absolutely do not want to do is add the two 45 degrees together to make it sine 90 degrees and give you the sine 90 degrees, which is 1, okay? Now, obviously, you should understand, because it's not 45 degrees being added to 45 degrees, it's the sine of 45 degrees being added to the sine of 45 degrees. So you need to work them out before you do the addition. So sine 45 degrees, we should be able to remember that, okay? So sine of 45 degrees, if you remember our triangle, if you can't remember how to do it, there was 90, there was 45 degrees. We said that was 1, that was 1, and that was root 2. So now we can see the sine of 45 degrees. So sine is opposite over hypotenuse. So the sine of 45 degrees is 1 over root 2. So that's 1 over, root 2 plus 1 over root 2. So 1 over root 2 plus 1 over root 2 is 2 over root 2. Okay. So just be careful. You're not adding the angles, you're adding the sine of the angles. And similarly, you could have a question that said, what can we have? Sine 30 degrees plus cos of 60 degrees. So we need to work the functions out before we do the addition. Yep, so let's remember if we can this one. So there's that. We have a 60 degree angle there and a 30 there. So remember it was an equilateral triangle, so we knew that was 2, that was 1, and that was root 3. So sine of 30, so sine is opposite. So 1 over hypotenuse 2, 1.5 plus the cos of 60. So that's adjacent over hypotenuse 1 over, so that equals 1. So they're the second sort of questions you might get as well. Oops, being a bit naughty here. We shouldn't leave an irrational on the bottom, should we? So we need to rationalise the denominator. So this should actually be 2 over root 2. So we need to rationalise that out. So we times both top and bottom by the denominator, which gives you 2 root 2 over 2, which gives you an answer of root 2. Okay, so yeah, always try and remember, as I forgot, to rationalise the denominators. Okay.